Wow, so many people here today. That's amazing. And nothing but black screens of death all around. I trust you're all alive and well.
Oh, no. Would you rather us be like?
Yeah,
like,
I'd rather see faces if it's possible.
All right. I don't know. I don't want to be the only one. I don't know if this was weird.
I mean, that's like when I walk into a classroom, would I rather stare at a black wall or see students? Probably students, other than, yeah. Hi, Katie. I'm not saying everybody has to undo their black walls of death. I mean, maybe you've chosen to get out of the shower and come straight to class, and that's totally fine. That's your deal. But yeah, I'm just telling you that professors love to look at students just because like human interaction is something that we are sorely missing in our COVID world at this point. Give me just a second. I'll be right back with y'all. There we go. Fresh. Wow, I am running paper like crazy this quarter. Let's wait about 1 more minute to make sure nobody else shows up. Okay. So last time that we were together, which was last Wednesday, unless you guys are in the in-person lab, which is on Friday. We covered everything that was in our schedule except
moles.
Except moles, right? So we looked over the organization of the periodic table. We talked about atomic number and atomic or mass number and isotopes. So the one thing that we didn't get to was this concept of the mole and molar mass. So we're that much behind, which is no big deal because there's like a makeup session that doesn't have anything in it scheduled every so often. So if we fall a topic behind every so often, no big deal because we'll just make it up in the makeup sessions. So the mole is one of the most fundamental concepts in the whole world of chemistry because the mole allows us to make a connection between the atomic scale, so what happens at the level of an individual atom or a small group of atoms, and the macro scale, what we could actually see or touch or feel or weigh out. All right. And this concept of the mole is something that we're going to be using for the entire year in the Chem 160 sequence. So because this is an Adams first textbook, we delay the discussion of chemical reactions and start with just what do atoms look like at the atomic level? How do they behave? And unfortunately, that leaves us with a lot of math that we don't really address for a long time. So our Atoms First book kind of tries to tuck a little bit of that math in earlier chapters. All right. So instead of waiting until like chapter 5 or 6 to start discussing this concept of the mole, our book does it in chapter 2 instead at the end. So the mole is really, and you guys will like this because we looked at them in chapter 1, it's just another conversion factor. All right. It's a conversion factor that we are going to learn 2 different definitions for. So the important thing is what it allows us to do, or how it allows us to connect what we can see and weigh out on a scale to something that has such an incredibly high number of individual things that we could never even possibly process that. All right. So let me give you an example of another thing like a mole that you guys are all familiar with. So when I see the word the dozen or a dozen, you know what that means. You know what a definition of a dozen is. It's a group of 12 individual things, right? So if I said I'm buying a dozen donuts, you know that means 12 donuts. If I go to the theme park and see a dozen giraffes, that means there are 12 giraffes out there in the theme park. Whatever the unit is, a dozen of them means there are 12 of them, right? So that is a group size that fits lots and lots of things. So instead of buying single donuts, we might buy a dozen donuts if we have a family and we like donuts. Now, the mole is just another group with a different size. So we know that a dozen is 12 individual things. Now, the mole is a group that is a lot bigger in terms of how many individual things there are in the group. The reason why it's a lot bigger a number is because we're trying to make a group big enough that we can actually weigh it out and it has some tangible mass. All right. And it turns out that a mole is the amount of a substance that has the same number of individual units as 12 grams of carbon-12. Now, it turns out that when we measure that number, there's a scientist named Amedeo Avogadro that made the earliest measurements of this number. At least to 4 significant figures, this is what he found out. That there were 6.022 times 10 to the 23rd individual carbon-12 atoms in 1 mole of carbon-12. All right. So how does this help us? It helps us because there's also another definition of the mole that allows us to convert into a mass that we would use on a mass balance. So I don't know that I've written this definition perfectly, but it's going to be close enough. All right. It'll be easier if we actually look at a couple of examples here. So if we have 1 mole of gold, I wish I had a mole of gold because it's worth a lot of money. First of all, gold is an element on the periodic table. So we could look up gold on the periodic table. Let's do that for a second. I have my periodic table right here. And here is our entry for gold, element number 79. Now, importantly, at the bottom there, you see gold's average atomic mass is 196.97. So I'm writing that down so I don't forget, because again, I don't have the whole periodic table memorized. So we know that 1 mole of gold, and I'll use its symbol instead, 1 mole of AU has 6.022 times 10 to the 23rd gold atoms in it. Right? That many individual atoms are 1 mole of gold. So 1 mole of any kind of atoms has 6.022 times 10 to the 23rd individual atoms in there. Now, it turns out that that second definition also tells us what the mass of that 1 mole of gold is. So 1 mole of gold, because gold's average atomic mass is 196.97 atomic mass units, a mole of gold has a mass of 196.97 grams of gold. So 196.97 grams. In our first couple of labs, have you guys weighed anything that was about that size? Anybody remember, for the people that were in person for labs? Our biggest beakers were kind of in that same size category, all right? So this 1 mole of gold is enough gold atoms that it constitutes a weight that we can easily weigh out on a balance in the lab. That is where the concept of the mole really has a lot of use, because there's no way that we could actually keep track of individual atoms when we're doing chemistry. They're too small. If we keep track of them in groups, though, like if we have a mole of each of the kinds of atoms that we're trying to put together, we should be able to pretty easily solve for how many moles of a product that we get out of a chemical reaction. So this is a way for us to track atoms in big groups all at once. All right. So for example, let's say that I have 25.5 grams of sulfur. Anybody ever weighed sulfur out before or seen it? You know what it looks like, the most common form of it? It's sometimes used as a like old school bug repellent / insecticide. It's not a very strong insecticide, but the reason why it is a good bug repellent / insecticide is because it's really powdery, so it sort of dries out and messes with their exoskeletons a little bit. So sulfur is a yellowish powder, is the most common way that you would find it in stores. It's often sold as sulfur flowers, which are little like pressed flowers that are pressed into a chunk of sulfur. And if you like squeeze on that chunk, it just breaks apart into a powder, and people use the powder for things, all right? So 25.5 grams of sulfur would be about the size of one of those sulfur flowers that you would buy at the store. But that is a mass that we could easily weigh out on a mass balance. The power of this mole concept is how we use it as a conversion factor. We could actually use the mole concept to figure out how many individual sulfur atoms there are in this piece of sulfur that we could weigh out on our balance. So how would we do that? Well, you've been given both the definitions of a mole that we can use as conversion factors. So we know that a mole has 6.022 times 10 to the 23rd individual atoms in it. We also know that a mole of any chemical formula is the number of grams we get by adding all the average atomic masses in that formula. So what does that look like for sulfur? Remember, for any chemical formula, just like with sulfur, 1 mole of sulfur has 6.022 times 10 to the 23rd sulfur atoms in it. All right, that's one of our definitions. And I'm introducing you here to the abbreviation for the mole. If you see a lowercase m with a dash over it, that means a mole. So 1 mole of sulfur has 6.022 times 10 to the 23rd sulfur atoms in it. The other definition, the number of grams we get by adding the average atomic masses in that formula. Well, let's take a look really quick. So right here is sulfur's entry on the periodic table. We see that its average atomic mass is 32.07. So that means that 1 mole of sulfur has a mass of 32.07 grams. We refer to that as the molar mass of sulfur. So sulfur has a molar mass of 32.07 grams per every mole. That's a conversion factor that allows us to convert back and forth between grams and moles for sulfur. All right. Now, if we had a different chemical formula, we would have to add up the average atomic masses in that formula to figure out how many grams there were in 1 mole of that formula. So if I start out with a number of grams of sulfur, using these two definitions, I should be able to convert into a number of moles of sulfur. And then I should be able to convert into a number of sulfur atoms. So these two definitions of the mole are just two new conversion factors that we can use to convert back and forth between grams of a chemical formula and moles of a chemical formula, and to convert back and forth between moles of a chemical formula and then individual units of a chemical formula. So for sulfur, because those are atoms, the individual units are atoms. So how would we set up those two steps? To convert from grams to moles, we would need our grams to cancel out. So our first conversion factor should look like this. To convert from moles to atoms, our second conversion factors should look like this. So now let's fill in what we know based on those conversion factors. We're starting with 25.5 grams of sulfur. We know that every 1 mole of sulfur has a mass of 32.07 grams. All right. By definition, the number of grams we get by adding the atomic masses in that formula. And then 1 mole of any kind of atoms has 6.022 times 10 to the 23rd atoms in it. So think about how simple this calculation is that we just did and how profound it is. All right. It's simple because it only took us 2 quick steps. All right. We basically have used both those definitions to do a quick conversion, and think about how incredible what we just solved for is. If we went to the hardware store and bought a sulfur flower, what we just calculated was how many individual atoms of sulfur were in that sample. We could count atoms. Every person in the entire world could count sulfur atoms as fast as they possibly could. We would never, as an entire species, be able to count all of those sulfur atoms in a lifetime. And instead, just using a couple of definitions, we were able to figure out how many individual sulfurs there were in that sample. All right, that's the power of the mole concept. Is it gives us a way to connect a mass of a chemical formula that we can actually weigh out on a scale to how many individual atoms there are in that sample. All right, so that's the mole concept. It ties together what we can see, a number of grams, to what we could never possibly see, which is how many individual atoms or individual molecules there would be in a sample. All right, so let's make sure we do the math correctly. And if you're a TI calculator user, here is how I do that next step. I'm multiplying by Avogadro's number, so times 6.022, and I'm going to use that EE function. So 6.022 E23 is TI calculator language for 6.022 times 10 to the 23rd. How many significant figures should I round to with this calculation? Hello, darkness, my old friend. Rudy says 3. So I see 4 sig figs in Avogadro's number. You can actually, it's known to more sig figs than this. This number you should memorize. We use it all the time in chemistry. So know that number, the number of individual things there are in a mole of something, know that to 4 sig figs. All right, 4 sig figs in our average atomic mass for sulfur, 3 sig figs in the number of grams of sulfur in that flour. So it looks like 3 sig figs is what we should know this to. So to 3 sig figs, that 4.788 times 10 to the 23rd rounds up to 4.79 times 10 to the 23rd. That's our number of sulfur atoms that there are in that sample of sulfur that we would weigh out on a lab scale. Pretty amazing that with just this simple definition, we can calculate the number of individual atoms in a sample. All right, Mia, question.
Hey, I don't, in your TI, you did 25.5 divided by 32.07. Why?
Because I divided by 32.07 in the first step of the calculation here. If it's in the denominator, I'm dividing by it, aren't I?
Yeah, I guess.
Why would I multiply by 1 first? Does that change anything?
No.
X times 1 is what? X, right?
Right.
So why would I put that into my calculator? I don't have to do anything with that 1 at all because it's not changing the quantity. So I just started by dividing by 32.07 because that's the first thing that's not a 1 that I came into contact with as I went left to right here.
Okay.
So when I set up these multi-step calculations, if it's in the denominator, I'm dividing by it. If it's in the numerator, I'm multiplying by it.
Okay.
So let's take a look at another one of these and see if you guys can figure it out for yourselves. All right. Anybody got a favorite element out there? I already let slip which one was my favorite element on the whole periodic table. It's sulfur. The reason why it's sulfur is because sulfur exists in more than 30 different allotropes, which means that when you find sulfur in nature, it could be in any one of a number of different forms. So that yellow powdery sulfur is one of those allotropes. There are a bunch of others. You can even make some yourself in the lab. So if I take that powdery yellow sulfur and heat it until it melts, and then cool it down very quickly by dropping it into cold water, it will actually crystallize as a different allotrope. So it'll be like an orangey, plasticky textured sulfur instead. So anyway, I love sulfur. It is awesome. All right, nobody has a favorite element. So let's do an element that is slightly different instead. All right, we'll do something that exists as a diatomic element. So if we find chlorine in nature, and there are some places that you see chlorine in nature, chlorine is an element that is diatomic, which means that it exists as Cl2. It exists in pairs instead of individually. All right. So those individual Cl2s are called molecules. A molecule is what we get when a small group of atoms is all connected by bonding somehow. All right. So later on, we'll actually see what Cl2 looks like in a little more detail. So this is called a Lewis structure for Cl2. And those two chlorines are connected by a covalent bond. All right. So that little group of atoms, those two chlorines, are a unit. We call that unit a molecule. So we should be able to figure out, anybody know what chlorine actually looks like? If you want to know what it looks like, then what you can do is you can dump a bunch of bleach into a toilet and then dump vinegar or some kind of stronger acid in there also. But don't do that because chlorine is super toxic and you will likely like gas yourself to death. All right. As a matter of fact, that has happened pretty recently. I think it was at a Buffalo Wild Wings a little time back. What happened was some people had used a strong bleach solution in the kitchen to bleach a floor with. Somebody else went back over that with an acidic cleaner that had phosphoric acid in it. The reaction of acids with bleach releases chlorine gas, and one person almost died and another person like died from exposure to the chlorine in a Buffalo Wild Wings. So when I said dump some bleach into a toilet and mix acid in, that's like literally what not to do. All right. Now, when I was a little kid and didn't know any better, I did that. All right. And I saw a little bit of chlorine gas coming out of the toilet. Maybe that's one of the things that ended up with me wanting to be a chemist someday, trying to figure out what happened. But chlorine gas has sort of a like greenish tinge to it. Okay. So, and it's a very useful gas for chemical reactions. It's also incredibly toxic. It's one of the first chemical weapons that was ever used. All right. So we don't want to make chlorine unless we know what we're doing and we have ways of limiting our exposure to it. All right. So let's say that we have a sample of 12.53 grams of chlorine gas, Cl2. How many moles of Cl2 do we have? And then how many individual molecules of Cl2 do we have? So if we were converting from grams of Cl2 to moles of Cl2, the definition that lets us convert back and forth between grams and moles of a chemical formula is we need the number of grams that we get by adding up all the atomic masses in that chemical formula. All right. So Cl2 is the chemical formula that we're trying to add up all those atomic masses. So right here is chlorine on the periodic table. 35.45 is chlorine's average atomic mass. But there are 2 chlorine atoms in this formula. So to figure out how many grams there are in 1 mole of Cl2, we have to add up those atomic masses for both of those 2 chlorines. So adding up the atomic masses of 2 of those chlorines gives us a total of 70.90. At least that's what I got when I did it in my head. So that's the number of grams of Cl2 there are in 1 mole of Cl2. Is anybody else getting the same answer that I'm getting? 0.1767 moles of Cl2 is the same size as 12.53 grams of Cl2. So just remember where these conversions come from, all right? 2 definitions of a mole. 1 mole of any chemical formula is the number of grams we get by adding all the atomic masses in that formula, all right? That's where this conversion comes from. And then if we're worried about how many individual atoms or molecules, all right, molecules here because there are 2 chlorine atoms in every unit of Cl2. So those individual units of Cl2, we call those molecules. So how many Cl2 molecules do we have? Well, if we have 0.1767 moles of Cl2, we know that every 1 mole of something has 6.022 times 10 to the 23rd individual units of that thing in it. So the individual units of Cl2 are molecules of Cl2. So think of Avogadro's number just like a dozen, right? If we have a mole of giraffes, we have 6.022 times 10 to the 23rd individual giraffes. All right, whatever those individual units are, a mole of those has 6.022 times 10 to the 23rd individual, those things. If you want to be entertained and dive into a mole hole for a little bit, search on the web for a mole of moles. All right, so this person tried to illustrate how massive the quantity would be if we took a group that was 6.022 times 10 to the 23rd individual moles, moles being the small mammal, right? So what would a mole of moles look like? Anyway, it's super entertaining, so you should definitely look that up. So it looks like in this case, we would have an enormous number of individual molecules of Cl2. Now that makes perfect sense. We're talking about a mass of Cl2 that would be pretty easy to weigh out if we had some way to trap that gas, all right? There are ways to trap and weigh gases, so that's an easy mass to weigh on a scale. We would expect that there would be a lot of individual little Cl2s that just contain 2 chlorine atoms each, right? We would expect there'd be a lot of those in 12.53 grams of Cl2. So let's try another one of these together, and I'll let you try and set this one up yourselves. And generally speaking, it will be a good idea for you guys to have some sort of copy of a periodic table available to you while you're in class. So I don't have to keep on showing you mine on the screen over and over again so you can actually see the problems. But for right now, I will try and keep both hydrogen and oxygen visible. So you can see hydrogen over here on the left and oxygen. Those are the 2 elements that make water, H2O. So individual units can be converted into moles. And moles should be able to be converted into grams. That's our plan. So by definition, 1 mole of water has 6.022 times 10 to the 23rd water molecules in it. And by our other definition, how many grams should there be in every 1 mole of water? Katie, you unmuted for a second like you're going to answer, and then you went, nope, not going to do it.
I think it's 18.02.
It is 18.02. Very good. So can you tell me how you got that number for the benefit of the rest of the class?
Multiplied hydrogens 1.02 twice and then added the 16 for oxygen to it.
So you added up the atomic masses of 2 hydrogens and an oxygen. All right, yep, 1.01 times 2 is 2.02. And then another 16.00 for oxygen. That's where we get our 18.02. Very good, Katie. And then we got to multiply this out. So my TI calculator language, it would look like this. So to 3 significant figures, I'm seeing 259 grams of water. Remember when we were examining the density of water last time we were in lab together, for those of you who did the density experiment, and for those of you who did the first online experiment, the first simulation, you can also calculate a density for water in that simulation. The density for water is really close to 1 gram per milliliter, which means that our sample of water here is like 260 milliliters of water. All right, very close to 260 milliliters of water. All right, now we're going to get one step more advanced using this mole concept. All right, not much more. This is about as far as we're going to go for now. We're going to use this a lot more later on, particularly this part of the mole definition, converting between grams of a chemical formula and moles. We'll use that all the time. The reason we don't use this one as often is because how often do we actually need to count individual water molecules? What reason would we have to know other than just like pure curiosity? How many individual waters were in a sample? How many individual water molecules? It's cool that we can do that, but in reality, most of the time when we're talking about actually working with chemical formulas, just converting to moles instead of into individual units like atoms or molecules is going to be close enough away for us to work with those. All right, so I'm going to give you a question, and then I think there may be a package at my front door. Did you guys hear that doorbell? Yeah, so I don't want to let that sit for very long because stuff has been disappearing in the neighborhood. All right. How many carbon atoms are there in a gram of sucrose? So sucrose is plain table sugar, and it has the chemical formula C12H22O11. How many carbon atoms are there in 1 gram of table sugar? So I'm going to give you guys a little bit of a clue. That's what the conversions are going to look like the way I choose to solve this problem. I'm going to convert from grams of sucrose into moles of sucrose. And then here's something that you're going to have to think about for a minute. How will we figure out how many moles of carbon there were in a mole of sucrose? All right, because that's the next conversion. And then finally, how do we convert from moles of carbon into carbon atoms? So take a couple minutes and see if you can figure out those steps. So to calculate our total number of grams in every 1 mole of sucrose, we would have to add up all the atomic masses in 12 carbons and 22 hydrogens and 11 oxygens. So based on this math, I'm calculating that every 1 mole of sucrose has 342.34 grams of sucrose in it. Are you guys getting the same thing? All right, so there's our first conversion. Every 1 mole of sucrose has 342.34 grams of sucrose in it. Now, how do we convert from moles of sucrose into moles of just carbon? All right, how many moles of carbon are there in this number of moles of sucrose? Well, let's take an easier question. All right, let's say I had just 1 molecule of water. How many oxygen atoms are there in this 1 molecule of water? How many oxygen atoms are there in there? Don't overthink it. Yeah, there's 1 oxygen atom, right? How many hydrogen atoms? 2. Okay. So what if instead of just 1 water molecule, I had 10 water molecules? Or let's say I had a dozen water molecules. All right, we'll go ahead and use that dozen group. If I had a dozen water molecules, how many oxygens do I have in there? That's an answerable question. If I have a dozen waters, how many oxygens are there in that dozen waters?
12.
Yeah, or a dozen, right? How many hydrogens are there in that dozen water molecules?
24.
Or 2 dozen, right? Okay, so if I have a mole of water, how many oxygens do I have in that 1 mole of water?
1
1 what?
gram.
1 gram of oxygen?
Okay, all right. Now I'm
What's the unit that we're talking about here? Moles, right? So we said that in a dozen waters, there were 1 dozen oxygens, right? So whatever the number of waters is, we have that same number of total oxygens because there's 1 oxygen in each water. Does that make sense? So if I have a mole of water, wouldn't there be 1 mole of oxygen in that 1 mole of water?
Yeah.
How many moles of hydrogen would there be in 1 mole of water?
2 moles.
2 moles of hydrogen in every 1 mole of water, right? Because no matter what the group size of waters that I have, however many of those I have, there are twice as many hydrogens as there are waters, because there are 2 hydrogens in each water, right? So how many carbons are there in sucrose?
12.
There are 12. So if I have 1 mole of C12H22O11, how many moles of carbon are there in this formula?
12 moles.
12 moles, because there are 12 carbon atoms in each one of these sucroses. All right. So since we have a mole of these, there are 12 times as many individual carbons as there are sucroses. So if there's 1 mole of sucrose, there have to be 12 times that many moles of carbon in that 1 mole of sucrose. And now that we know how many moles of carbon we have, we should easily be able to convert into carbon atoms, because Amadeo Avogadro tells us that there are 6.022 times 10 to the 23rd individual things in 1 mole. So here we're talking about carbon atoms.
Wait, okay, I feel really good. All right, this is clicking now.
It takes time.
Yeah.
So that's the big thing that I want to introduce you guys to today, is what the definitions of a mole are and how we use them to connect an amount of stuff we can see. We can weigh out a gram of sugar very easily on a kitchen balance, all right? And here, in just a few steps, we've calculated the number of individual carbon atoms in that 1 gram of table sugar. Pretty awesome, powerful technique. Most of the time, the conversion factor that we're going to use in the world of chemistry the most is converting back and forth between grams of a chemical formula and moles of a chemical formula. We'll do that all the time, all right? That is going to allow us to do lots of things with, for example, if we're running a chemical reaction, we can use this kind of math to figure out how many grams of reactants we need to put into the reaction if we know how many grams of products we want to get out of the reaction. So it allows us to plan for chemical reactions to make sure that we're using enough of our starting materials, of our reactants, to get the number of products that we want out. The same way, like if you wanted to make 30 sandwiches, you'd have to plan ahead and say, in order to make 30 sandwiches, I know I'm going to need at least 60 pieces of bread to make that work, right? So that kind of planning is the same kind of planning that we do when we calculate number of moles of each one of our things that we're putting into a chemical reaction. It allows us to figure out how much of our products we can make from that kind of math. All right, so that's our sneak peek as to why this is important. But for right now, just being able to use the mole concept to convert from grams to moles of a chemical formula, or from moles of something into individual units of something, that is the level of introduction that we're looking at the end of chapter 2. Wow, I missed like a crap ton of stuff in the chat. Sorry, everybody. And I'm just getting like bunches of numbers thrown in the chat. Okay. So Rudy, you were definitely on track with the number of moles of carbon in a mole of sucrose, which is awesome. All right. So remember, a mole is just another group size. If we're talking about dozens, if there were 100 sprinkles on each donut and I had a dozen donuts, I would have 1,200 sprinkles total, right? Because 100 sprinkles on each dozen or on each donut, and there are 12 donuts in a dozen. It's the same basic idea, is we're grouping these atoms. It's just the group happens to be a ginormous group because atoms are really tiny. I would like to, well, I'd like for us to be done right now, but we can't be because we have to keep on going and start to talk about the chapter 3 topics that have to do with light. All right. So if you're watching chapter 3 videos, what you'll figure out is that light and how light behaves when we use it to shine on atoms, that is really a lot of how we figured out how electrons behave, is by basically taking samples of atoms and shining light on them and then measuring what happened to the light when the light was released from those atoms. So that is called absorbance, or now I wish that I had the samples at home to do this. For those of you who are in person, I'm not even going to bother you with absorbance because it's too advanced for us right now. This week for our in-person lab, those of us who are in the lab are going to see what happens when we excite, when we add energy to samples of different atoms. And generally what happens is they give off light. All right. So if you look up and you have a halogen light bulb in your house, what you're seeing is electricity, like electrical energy, being passed through a sample of some kind of sample of atoms. All right. So halogen lights, it's some halogen, probably chlorine. Right. You can also have neon lights, and in neon lights, guess what? The sample that you're passing the electric current through is neon instead. So when samples of atoms are excited by passing energy through them, they give off light. And that light has specific properties to it. That light, just studying what that light looked like that atoms give off when they're excited, actually was a key for us to figuring out a lot about the behavior of the electrons in these atoms. All right, so a very simple experiment, but if we pay careful attention enough to what that light looks like that's coming out of those atoms when we excite them, it actually tells us something really important about those atoms. So before we can understand the stuff that's important about what that light tells us when it's given off by atoms that are excited, we have to understand just like about light in general. So the behavior of light is very interesting because light behaves in lots of ways, or in lots of ways like a wave. All right. It's hard for us to measure the mass of light directly. So light is not a traditional object that we can go and put on a scale someplace. All right. We can't see a piece of light. So for those reasons, it makes a lot of sense for us to classify light as a wave in the way that it behaves. So when we're talking about the properties of waves, this equation is an equation that sort of encapsulates the behavior of waves, generally speaking. So if we're talking about how fast those waves are going, all right, So in this case, if we're discussing light, that speed is the speed of light. We'll talk about that. It's actually a physical constant, something that we can remember. And these are both Greek letters. This one being lambda, that one being nu. So the speed of light is equal to the light's wavelength times its frequency. Now, the units for speed of light that we're going to be using in this class are meters per second. And that's a constant that we can just stick in our head and remember. It turns out that the speed of light, at least in a vacuum, is 3.00 times 10 to the 8th meters per every 1 second. So that many meters is how far light travels in every 1 second. If you're interested, you can actually read about the experiments that scientists have used to estimate or measure the speed of light. So some of them have literally been like shining light from a distant mountain to another distant mountain that were hundreds of miles away and making careful recordings of how long between when the flashlight turned on and when the light was observed at the new place. Pretty neat, all right? I mean, it seems simple, but when something travels that fast, it's not like clocking somebody going through a school zone, right? It's harder for us to measure something this fast than it is to measure a car going 10 miles an hour too fast in a school zone. So the experiments used just to figure out that speed. Pretty interesting experiments. We're not going to go through all of them right now because we don't have time. Now, what about wavelength and frequency? If we're talking about wavelength, if light is a wave, then waves tend to have this sort of sine-like shape to them. And the wavelength is the distance that we get going through one entire wave cycle. So from here to here, that is one wavelength of this light. We could also measure that one wavelength from a crest to the next crest. That is the same as this distance if I've drawn this well, or from a trough to a trough. All right, so the distance that we traverse by going across one complete cycle of the wave, that's a wavelength. Now, there are also other things that we could look at on this little graph, all right? We could talk about the amplitude of the waves. So the amplitude is like how big the peaks are. If you think about a physical meaning for amplitude, think about it like volume, all right? For radio waves or for sound waves, the taller those waves are, the louder the volume that you get on your ears, all right? That's amplitude. Frequency is not something that is in this picture anyplace. And the reason why is because frequency has to do with the motion of these waves. And this is just a picture of the wave not moving. So imagine like this would be a photograph that I took at the beach of those waves out on the ocean. Why can't I tell the frequency of those waves? Because I can't see any of the motion in this picture. All right, so the frequency of the waves on the ocean might be measured like how many waves hit the sand every minute, how many waves hit the beach per minute, right? Waves per minute, that's a frequency. It tells us how many waves pass a given point per every unit time. And the same thing is true here. It's just these waves are moving a lot faster. So we're talking about a frequency in number of waves per second that pass a given point instead. So if I'm thinking about the units in this equation, I'm thinking about meters per second for my speed of light. The wavelength is a distance in meters. The frequency has to be in units of 1/seconds or inverse seconds. So how do you have a unit of per second? Well, think about what we just said about the waves at the beach. It's number of waves that hit the beach per second. So if my frequency were 12 here, then 12 waves would be passing a given point per second. So very often frequency, so 1/seconds, can also be written as seconds to the -1. That's units for frequency, and they're often also given the name hertz instead. So hertz is a unit of frequency that is seconds to the -1, the number of waves that pass a given point per second. Basically, the way that we use this equation most of the time is if we know any two of these variables, we can always calculate the third. All right. So if we know the wavelength of light that we have, we can calculate its frequency. For example, visible light begins at a wavelength of about 400 nanometers. What's the frequency of this light? I'm going to zoom out a little bit so you can see everything that I've written so far. So visible light begins at a wavelength of about 400 nanometers. What's the frequency of that light? So we know the speed of light is always 3.00 times 10 to the 8th meters per second. We also know that the wavelength of light at the low end of the visible spectrum is like 400 nanometers. Be really careful when you solve for the frequency that your units cancel out correctly here. All right, this is a unit cancellation kind of issue. So the reason why this is an issue is you can see our wavelength is in units of nanometers, but our speed of light is in units of meters per second. So if we want to figure out the frequency of this light, then our wavelength has got to be in meters instead of nanometers. We're going to have to convert that wavelength into meters instead of nanometers. So make sure that you can do that. Oh, Rudy pieced out. Rudy, good night. It was wonderful to have you around for a while. So in order to use this wavelength of 400 nanometers, in order to solve for our frequency, nu here, we're going to have to convert those nanometers into meters first to get our units to cancel. So 400 nanometers. We know that every 1 meter has 10 to the 9th nanometers in it. So it looks like our wavelength in meters is 4.00 times 10 to the minus 7 meters. So has anybody calculated a frequency yet? I'm getting a frequency of 7.5 times 10 to the 14th hertz, or seconds to the minus 1. Note that that's the unit left over. If these are meters, this has to be seconds to the minus 1. So meters times seconds to the minus 1 is meters over seconds. So what that means is those waves of light at the low end of the visible spectrum, 7.5 times 10 to the 14th of those waves pass a given point per every second. All right, that's what it tells us about those waves. So if you've never heard of the visible spectrum of light, let's take a quick look. Not only that, but some other types of light that you might recognize or you might not. Here's a nice picture. Something very similar will be in your book also. Now, these are different types of light. And out of all these types of light, from the most energetic down here, all right, notice that they're talking about the wavelength of this light. And here on this side of the spectrum, the wavelengths are really, really short. And over here on this side of the spectrum, the wavelengths are really, really long. All right. So gamma rays and X-rays, it turns out, are very, very energetic light and short wavelengths. UV light, still very short wavelengths. We know UV radiation can be damaging to our skin, right? So still this light is fairly high energy. And then less energetic than UV light is the visible part of the light spectrum. So this small band of light with wavelengths between 400 nanometers, which is like on this side of the spectrum, and about 700 nanometers on this side of the spectrum. Those are the wavelengths of light that our eyes can actually process. So not very much of the total light spectrum. The cool thing is that biologically, that we're not unique in terms of, or we don't have the exact same wavelengths visible to us that all other creatures have. Some creatures can see a little bit farther into the UV. Other creatures can see a little bit farther into the infrared part of the spectrum as well. So just because our eyes can process stuff between 400 and 700 nanometer wavelengths, that doesn't mean that all eyes process wavelengths that are equivalent to that. All right, interesting. And then even longer wavelengths are the radio waves, the same waves that our towers use to move data around with longer wavelengths. So interesting. Now, we don't have time to go through all of the experiments today, at least, that went into our understanding of the behavior of light, all right? But there's considerable evidence that light also has sort of particle behavior to it, all right? In other words, there are ways that we can think about light behaving as like discrete individual little pieces. So we call those pieces of light, it's not like we could like trap one in a box someplace, although scientists have tried to do very similar things to that. We call those individual pieces of light photons of light. And it's important for us to think about what a photon of light is, because we can, through a physical constant that I'm going to introduce you guys to, we can talk about how energetic a single piece of light is. So the energy of a photon of light is equal to Planck's constant times the light's frequency. Now, why is this important? Because some types of light are more energetic than other types of light. So what makes it more hazardous for us to get hit with gamma rays than to get hit with visible light? All right, so if we shine a red light that, Mia, do you need to have that blown up a little bit? I see you squinting a little. How's that, better? The energy of a photon of light is equal to Planck's constant times the frequency of that light. So this explains why if I were to shine a flashlight on my skin, I could do that for hours, no problem at all. All right, visible light, it's not going to hurt me. Now, if I shined a UV light on my skin for 5 minutes, I could give myself a sunburn. All right. If you go to a tanning bed, what you're really doing is you're using UV lights to cook your skin a little bit. So if I went to a tanning bed for 15 minutes, I would be a lobster. And I would also be statistically increasing my chances of skin cancer, because that light is energetic enough to introduce mutations into those skin cells at the DNA level. All right. So the light is energetic enough to break some covalent bonds. And when that happens, the new bonds that form aren't always the right ones. So what ends up happening is we introduce errors into our genetic sequences, all right? And that can result in cancer. If you think that UV light is enough to do some damage, and it is over time, then X-rays are even more energetic. So think about X-rays as light that, I mean, it's still light, so it's still moving at the same speed, but it has a much shorter wavelength. So each of those individual packets of X-ray light contain even more energy than the individual packets of UV light. So when one of those photons of X-ray light hits a cell, that's really enough to break a covalent bond. And even worse than that, gamma radiation, all right? Light in the gamma region of the spectrum has even more energy. So the cool thing about when we talk about radiation, radiation is just like light, essentially. There are other particles besides just light that are released in radioactivity, but a lot of times what we're measuring when we measure radioactivity is just the presence of gamma rays, for example, like light that's being released from a radioactive sample as it decomposes. All that is just high energy light. It's high enough energy that those gamma rays can pass through almost anything, all right? Most major cities have radiation detectors to see if somebody were trying to bring in like some sort of a radiological bomb to detonate in the city or something. Major cities have these passive detectors. What are they detecting? They're detecting gamma rays. So if somebody has a sample that's putting off lots of gamma rays, even a couple of miles away from a city, those gamma rays will travel that far easily, passing through trees or buildings, whatever, because that light is so high energy, all right? So what can we tell from this equation? We can tell that the bigger our frequency of light gets, the more energy it has, because this H is just a constant, all right? So the higher our frequency of light, the more energy our light has. So I can give you the constant. H, Planck's constant, is 6.626 times 10 to the minus 34 joules times seconds. Also, if you want to just nerd out about Stranger Things for just a second, in the third season of Stranger Things, Planck's constant makes an appearance, all right? That is the combination of the Russian safe that they need to get into for some reason later on in the episode. So anyway, that number shows up in this equation and lots of places in the world of physics as well. So we just figured out the frequency of that light that had a 400 nanometer wavelength. Let's figure out how much energy a photon of that light had. All right, we figured out that our frequency of that light was 7.5 times 10 to the 14th seconds to the minus 1. So let's keep on rolling and see if we can figure out how much energy a photon of that light has. And all we're doing is substituting in what we know and canceling units. So if we're solving for energy, Planck's constant is 6.626 times 10 to the minus 34 joules times seconds. And our frequency of that light was 7.5 times 10 to the 14th seconds to the minus 1. What do we get when we multiply joules times seconds to the minus 1? What do those units cancel out to give us? Aren't seconds to the minus 1 the same thing as 1 over seconds? They are, right? So seconds times 1 over seconds, those two units cancel each other out. So we're left with just joules for our unit, and joules are a unit of energy. Also, Dr. Musk was slightly dumb. Let's go backward a little bit because this has 3 significant figures in it. That wavelength has 3 significant figures. I only reported 2 sig figs for my answer here. You guys should have read me the riot act and said, Dr. Musk, why didn't you report 3 significant figures for that answer? It's perfectly acceptable for you to do that. So if that's the case, and I actually have 7.50 times 10 to the 14th inverse seconds for my wavelength, or sorry, for my frequency, then it looks like my energy of that photon of light would be 4.97 times 10 to the minus 19th joules. So why do we calculate an amount of energy in each little photon of light? Because those individual photons of light are what interact with atoms. So when we're thinking about how light and atoms interact, if we're thinking about how an atom can be excited, sometimes atoms can be excited by absorbing a photon of light. And what that does is it does something to that atom's electrons. All right. Sometimes atoms can release a photon of light to relax after they've been excited. So we're not going to get into how exactly that works yet. That's a next time thing. But the reason why we're worried about how much energy there is in a single little piece of light is because those pieces of light, those photons, are actually what are interacting with individual atoms in a sample. We're at about an hour and a half in. That's probably enough for us for tonight. So on Wednesday, we will do some more practice using these 2 equations that talk about the behavior of light. We're also going to talk about these things called atomic line spectra. So make sure that you watch the video about atomic line spectra in chapter 3, because this experiment, taking an atomic line spectrum or seeing what an atom gives you back for light when you excite that atom, that tells us so much about the behavior of the electrons in this atom. We don't have time to go through all the experiments that got us to figuring out what these atomic line spectra actually represent, but this is what tells us everything about the behavior of those electrons. All right. For those of us doing in-person lab on Friday, we're going to be looking at the atomic line spectrum of some different atoms. For those of us doing the simulation, you're also going to be doing the same thing. It's just you're going to be doing the simulated version. In this case, you're not losing a lot one way or the other. All right. You're seeing with your eyes or you're seeing on a computer screen. You're seeing the same thing either way. So for Wednesday, make sure you watch the videos about atomic line spectra, and we will pick up our discussion then. Any questions? Is everybody able to access their labs okay? I've been getting like emails about students not being able to access files for the lab, and it may be just my 121 students, or it may be some of you guys. If you're having problems with accessing any of the resources on the course, please text me or stop by my office hours and I'll help you, okay? Because I don't always know that students are having access problems until like I got a couple of emails on Friday night and people were like, I'm having problems accessing the homework for chapter 1. And I'm like, but it's due in like a half an hour. You know what I mean? I'd have a lot easier time helping people if they let me know a little more ahead of time that they were having problems. Okay. So just let me know if you're having problems. That's the real take home message. Any more questions before we're all done? Thank you guys for hanging out with me. I appreciate it.
Good night, Dr. Musk. Good night, guys.
Mia, MRIs are you saying, are they similar to what?
Like x-rays, as far as like, are they harmful?
No, MRIs are not harmful at all. So MRIs do use light, but they use radio waves instead.
Oh, Okay,
Yep.
that's on the opposite.
Yep. So the radio waves are very low energy, right? That's less
Yeah.
energy even than shining a flashlight on yourself.
Right.
So
Okay.
the exact way that MRIs work is like pretty far beyond the concepts that we're going to go over in this class. But if you're going to major in chemistry, or you're going to do enough chemistry to take the majors level 200 series organic chemistry next year, you will learn how MRIs work, because there's an instrument in the world of organic chemistry that works almost exactly the same way, called NMR, nuclear magnetic resonance spectroscopy.
All right. I guess I'll learn about it next year then.
You will, or if you want to come by office hours, I can teach it to you. It's just not something that we have time to go over now. So basically it uses radio waves, and also besides these radio waves, it uses really, really powerful magnets. And what the magnets do is they induce all of the nucleuses of the atoms in that sample to all orient themselves with a specific spin state, is what they call it. So anyway, nuclear magnetic resonance, right? We're actually making the nuclei, the nucleuses of all the atoms in that sample sort of line up in and resonate in a certain orientation. And
That's
then
cool.
the radio waves do something to those nuclei that lets us tell something about those atoms. So it's actually the most powerful technique that we have as organic chemists to be able to figure out what the structure of our molecules is that we're looking at. That's one of the biggest things in chemistry, is like, when I did this chemical reaction for the first time, what did I make? What happened, right? So what is the structure of the stuff that I made in this chemical reaction? And NMR is one of our biggest tools for answering that question in organic chemistry. And it works on exactly the same principle as MRI does. So pretty neat. Also, the scientist that invented the whole concept of NMR/MRI, he was a scientist that worked at University of Illinois, where I did my PhD. And he was still there, and like only maybe 10% there because he had Alzheimer's. Like he was sorry, it happens. People get old, right? Dementia is a thing, and it's like a real part of life for some people. But he was at one time like one of the most brilliant scientists in the entire world. And he was still at University of Illinois, puttering around his office, you know, in his late 80s when I got there. So anyway, yeah. Yeah. All
I
right,
didn't
y'all.
realize you were an Illini.
I am an Illini. Yep, that's where I got my PhD, was at University of Illinois.
I started at Southern Illinois, but
Carbondale?
Yep. I contemplated Illinois.
Sweet. That's really awesome. Yeah. The only reason I know Carbondale is because while I was at University of Illinois as a graduate student, I fished for the University of Illinois' competitive bass fishing team.
Nice.
Southern Illinois had a team also, and we had a tournament that they hosted at Lake of Egypt down there. So
They still do it.
I won that tournament. It was awesome. It was a really good tournament. I figured out something really special about what the largemouth bass were doing that weekend. So I caught bigger ones than everybody else did.
Oh, the ringer, the shark.
If you go down the Google hole far enough, you might be able to find pictures. So it was 2006 that University of Illinois won their first Big Ten bass tournament.
Mhm.
And I was the one who caught the winning stringer of fish for the whole tournament.
Oh, wow. That's awesome.
So you're looking at a Big Ten championship athlete.
Love it.
Awesome.
All right, you guys have a wonderful night. I'll see you
All
Wednesday.
right, you too.
Bye.